Hello, today I'm going to go over calculating solar input at different latitudes area formula. And what we're talking about here, we see the Earth and we see sunlight coming into the Earth's atmosphere and striking the surface of the Earth. Well, because of the angle, not all areas get the same amount of energy per area. What I mean by that is here at the equator, the sun is coming straight in. It's coming straight down to the ground. And so this area here that it's hitting, we can compare to this area up at the North Pole. At the North Pole, you see it's coming in at an angle. So it's entering the atmosphere at an angle. And it spreads that out over a larger area. Same amount of energy, larger area. And that's why the North Pole, one of the reasons why the North Pole is so much cooler than the equator. So let's do some calculations so we can actually see that. So we're going to come down here. I've got two locations, one at the equator, 0 latitude, and then one location up near the North Pole. We're going to be calculating area, and for me, for pi, you can just use 3.14. That's fine. And what we see at the equator, the radius for the area that we're measuring ends up being 1.3 meters. Well, up near the North Pole, that area is spread out. Remember, it's bigger because it's coming in at an angle. So it's actually at 2 meters. It's larger. So let's calculate the area here. 3.14, which is pi, times the radius, 1.3 squared, equals 1.3 squared times 3.14. And I'm going to round this to the first decimal place. So I'm going to have 5.3 meters squared. And then down here, I'm going to use 3.14 again, put my radius of 2 in there. We're going to square that. So 2 squared is 4 times 3.14. Equals 12.6. Remember, I'm rounding that. And so I've got an area now. And we see that the area is much smaller at the equator than it is at the North Pole, right? Now we're going to take the amount of energy that's coming in at those locations, which is 5,400 watts for both, and we're going to divide them by the area. So this is 5.3 and this is 12.6. And for this first one, I'm gonna round it to exclude the decimals. So I have 1,019 because I rounded up. And then for the next calculation, I have 429, again, rounding up the decimal. And this makes sense with what we just talked about up here, namely being that the watts per meter at the equator is much higher, more energy in a smaller space than it is at the North Pole. It's really the same amount of energy, but we have a bigger area, so it's spread out. Let's do one more, at least this first one. So I'm changing the latitudes a little bit, but you'll still see basically near the equator and basically near the North Pole. And I've got my radiuses here. So let's do 3.14 times 1.2 squared equals 1.2 squared times 3.14 equals, in this case, we're going to go to 4.5 meters squared for rounding. And I'm going to move this number over here, 4.5. And I've got a new amount of watts because we have different energy calculation now. 4450 divided by 4.5 equals 980 9, because I rounded it. And you're going to do that for this next one, and you can compare the two. And for all of these, what you should see is a larger number if it's closer to the equator, and a smaller number if it's closer to the North Pole. All right, I hope this helps. Thanks.